This is a wonderful place to be. I am really thankful to the organizer for giving me a chance to speak louder. Okay, today I'm going to talk about thin and thick disk of spiral galaxies and their formation. And on the left, you have a snowflake. If you have a small snowflake in the air, then we all call it beautiful. But if you have a gigantic snowflake floating in the space without any external environmental effect, then it'll be a subject of mankind, which is the case, right? We have spiral galaxies, which is the majority of the universe. And then apart from the spiral arms, we see a laser thin structure, and they are floating in the universe all by themselves. And this should be an issue to mankind. And thanks to many advances, including cosmology, now we can reproduce some of the key observables of galaxies ab initio from the CMB anisotropy. This is actually a great achievement. And so now we want to see whether we can actually reproduce thin and thick disks as well as just overall morphology of galaxies. So first, I'll talk about thin disk. Before doing that, I will introduce briefly the simulation I'm using. It's called New Horizon. It's mainly the IAPE effort, and then I have added a little bit of effort to that as well. It's a cosmological zoom-in simulation on a small region from the Horizon AGN simulation, and it's about 20 megaparsec diameter, so it's small. It has about 150 galaxies above 10 to the 9 solar mass, so it's a small volume, medium-sized volume simulation, but we aimed at a very high resolution, 35 parsec. It's about 30 times better than Horizon AGN, and probably about a few times better than TNG50, and probably twice larger than Wintergarten, if I'm correct. And the mass resolution is about 10,000 solar mass, so it's comparable to Wintergarten, but about 100 times better than TNG50. We burnt a lot of computing time and reached Z of 0.17, and only to realize that we didn't really have the chemical elements in detail enough. So later I ran New Horizon 2, a sibling with a little bit of poorer resolution, but including all the chemical elements to study galactic structure a little bit better. All right, so this shows you a sample galaxy in New Horizon in SCART. So we did a post-process to make mock images. On the left, you have, it's basically the same galaxy shown in two different viewing angles. But in the beginning, they don't really look like galaxies at all. It's just a blob, 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 blob. At some point, with some influence from the neighborhood, maybe cosmic web, I must say at least once in this conference. And then now you begin to see a beautiful disk developing at some point. And unless there is further perturbation through major mergers, then this will maintain its disk beautifully, just like this. All right, so rough comparison. On the left, you have observing data and the New Horizon and TNG50. So now finally, I think we can study the vertical structure of these galaxies, which was the main aim of the New Horizon simulation from the beginning. So this gives you a sample fit, a radial fit and a vertical fit to this galaxy, and both radial and vertical fit tell us that we can reasonably well fit the overall profile using two components, so bulge and disk, and then thin disk and thick disk. So not bad. And then we can witness the emergence of the disk. So from high redshift, it doesn't look like a disk galaxy. At some point now, you have a very fat disk, and later you have a laser thin disk. And in circularity parameter, in the beginning, you have dispersion dominant system. Suddenly, all of a sudden, you have a rotation dominant system. So now we call this an epoch of disk settling. So if we use the observer's technique of using V over sigma gas greater than 3 as a criterion for settled disk, and then we find for these Milky Way sized galaxies, about 30 of them, and roughly half of them have a beautiful thin disk at redshift around 1.5. So it takes actually quite a long time for galaxies to develop galactic scale large disk. And if we use theoretician's method, i.e., if you define disk settling redshift as the moment where 80% of the young stars are formed on a rotating thin disk, at least for 5 consecutive snapshots, then most of these settled disk galaxies have mean mass of about 10 to the 10th solar mass. So it takes a long time for a galaxy to develop a disk. This is a big problem because JWST has already found disk galaxies much earlier and having much smaller disk. So maybe there is a little bit of a resolution problem. So to sum up on the thin disk and disk settling, galaxies should be massive enough and having collected enough angular momentum from the cosmic web to develop a galactic scale disk and reach a metastable stage with Tumray-Q parameter around 1. That was briefly mentioned by Chris on Monday. And major mergers disturb the system. So if you have a lot of major merger, usually in the early universe, then it's very bad for settling disks. And too much stellar feedback is very bad as well. So that's usually what happens in the very early universe when there is a lot of gas-rich mergers, right? So it makes sense that it takes time. You know, I will probably bet my money on epoch of disk settling to be a Z of 1.5, but it actually takes quite a bit of time anyway. The second topic is on the thick disks. As you can see here, you see some thick disk, right? So it was first addressed by Gilmore and Reed in 1980s, and then there seemed to be a break in the vertical structure. And then people talked about thick disk ever since then. And initially it was fitted with exponential function, and the vertical scale height is about a factor of 2 or 3 between thin and thick disk. And about a tiny little fraction, mass fraction, seems to be in thick disk in the beginning. And later people realized that the hyperbolic secant phi function reproduces the distribution a little bit better. Now the thick disk fraction becomes a little bit larger than that. And then later, Bovie and Ritz and the collaborators realized that actually you can't really use the observed star counts directly. You have to do a little bit of modeling to reveal the true mass ratio between thin and thick disk. And now they have 6 to 1, the thin disk dominant by a factor of 6. Okay, these are what have been found. And orthogonally now, no, actually not orthogonally, in parallel, observers using spectroscopic methods found that actually there is a sort of bimodal distribution in alpha over Fe among the thick disk, among the disk stars. And then they interpreted that the high alpha blob probably tells us about the thick disk. If you believe this, then the ratio between thin and thick is 2 to 1, not 6 to 1, not 225 to 1. So now we are puzzled. And also the bimodality, apparent bimodality, could be interpreted as a sign for distinct origins between the thin disk stars and thick disk stars. And then observationally again, for external galaxies on edge-on disk galaxies, people used the vertical surface profile fits and then found that the scale height difference between thick and thin is roughly about factor of 2 to 3, just like Milky Way. And then the luminosity fraction of thick disk is between about 10% all the way up to about 100%. So there is a wide variety of thick disk fraction. So the formation scenario was questioned. So the first one is disk heating. So if you have a thin disk and the stars born on the thin disk will be gradually heated through many perturbations, or maybe radial migration. Some of the stars will migrate radially, and as a result, they will be elevated as well. Sometimes accretion, so the disrupted satellite galaxies can be populated as thick disk, or maybe a gas-rich galaxy merger, or maybe accretion can cause some in situ star formation in the position of thick disk, away from the mid-plane. Okay, so there are many scenarios. All of them make sense. So this is our New Horizon galaxy. Now the question is, do we see such thick disks in New Horizon simulation? And if we do see them, then what is the origin, at least in this simulation? This is a JK's, my students' Gaussian mixture model. So applied on this galaxy, the same galaxy, and then we do the kinematic analysis using energy and two components of angular momentum, and then machine learning technique finds distinct kinematic components. In this case, 6 components, but you can use any arbitrary number of components. In this 6-component try, it detects thin disk and 2 separate components of thick disk and 3 other spheroidal components. Okay, so maybe there are distinct components. And then we do the profile fitting to derive the vertical scale heights of thin and thick disks, a factor of about 3, which is exactly found in Milky Way. And then compare with other galaxies. So here on the left, you have the vertical scale height ratio between thin and thick, roughly about 3. New Horizon galaxy is now in gray band. It's in good agreement with Milky Way and all the other galaxies, external galaxies. All the others are the observational data, and the New Horizon is the gray band, based on about 20 galaxies here. And the thick disk luminosity fraction, I mentioned that it's between 10% and about 100%, and New Horizon covers or maybe reproduces the range reasonably well. So that was actually the answer to one of the questions after the previous talk. And now we focus on the mid-plane stars. Now I call them thin disk. Maybe this is wrong, but anyway, geometrically thin. And then off-plane stars, now I call them thick. Okay, this is a little bit wrong, but just geometrically thin and thick disks. And then compare them in various stellar properties based on these 18 galaxies. Thin disk is a bit younger, as expected. Metallicity a little bit richer, as expected. And the fraction of stars coming from the outside, is negligible, about 10% or less, both in thin and thick disks. All right, now, because I was able to do the New Horizon simulation, the second version, using chemical elements, now I can show you alpha enhancement as well. And you know, that was a puzzle, right? Observers found bimodality in alpha over Fe versus Fe over H distribution. And then the clear bimodality, does it tell us the clear 2 distinct origins of thin and thick disks? Okay. So here, I show you just one galaxy, and we have many, but one galaxy. Just like in Milky Way, we have one large alpha blob and one low alpha blob, bimodality. And alpha over age diagram, now this is the thin disk component, presumably, and there is a higher alpha blob, which was actually produced by a recent merger, exactly as Florent just suggested. And if we look at other galaxies, we have many other galaxies. They all have different alpha versus ion morphology in this diagram, because they all have different merger history and star formation histories. Okay, so we can't really generalize the picture based on one galaxy. And now we go back to the first galaxy I showed. So again, now after a little bit of smoothing, you have a clear bimodality. Now if you look at the high alpha stars, yeah, indeed, it's thick. And if you look at low alpha stars, then it's very thin. Bravo. So observers were all right. And now you go to the circularity distribution for the alpha. So the low alpha blob, yeah, indeed, it's really, really thin disk component, high circularity, orbiting very, very fast on the thin disk. But if you look at the high alpha star particles, you have a wide variety of circularity, and actually even the peak is on the fast rotating thin disk component kinematically. So alpha can be a very good hint or maybe tracer, but it cannot tell us the full story. Okay, 5 minutes, thank you. And now what about the spatial classification, which I applied earlier? So spatially defined thin and thick disks. So mid-plane, I call them thin star particles, and off-plane thick, right? And now this one is the thick component, a thin component, and that's a fitted thick component. If you do this in the thick, spatially thick component, there is hardly any contribution from the thin component. It should be the case, right? So the contamination from the thin disk stars is under 10%, and contamination of the thick disk stars in the mid-plane is also under 10%. Good, very good. But when we actually look at the star particles in the thick disk and thin disk regions, spatial regions, actually now they have a fair bit of overlap in the circularity. So the spatial, vertical or radial, any kind of surface brightness fits can give you very good hint on the original or maybe the true structure, but does not tell you the full story. Actually, it's very, very contaminated. Disk to total ratio, V over sigma, whatever is visible in your observed MOOC image is heavily, heavily contaminated if you believe the kinematic structure is the true value. All right, now what about the birthplace of these thin and thick disk stars? So here in one galaxy, so this is the galactic center. So these are the currently thin disk stars, that's currently thick disk positioned stars. And if you look at their birthplace, their mean birthplace is on the thin disk. If you look at 18 New Horizon galaxies, all of them are born on the thin disk, and then all of them are elevated to be thick disk component later on due to varieties of physical processes, including disk heating, even if there is no series merger. If there is merger, it helps greatly to heat the disk. Okay? So this sums up a little bit. So this is the present day's circularity. This is disk, and that's dispersion dominant, and the circularity of birth. At the birth, most of the stars are born on the thin disk, low, high value, but as time goes on, many of them become thick. Okay. Oh, this is another way of telling you this, a little bit complicated, so I'll just skip it. Christoph loves this diagram, but I will just skip it. So the summary is both thin and thick disks are very well reproduced. Do I believe my models? Well, only half. So I still think there is a lot of resolution issues, even with 35 parsec. And thick disk stars are mostly in situ formed. So of the a few scenarios I mentioned, so external origin, XC2 origin probably can be reasonably ruled out, even considering the resolution issues. Thick disk is mainly a result of circular evolution. I don't know what I mean by circular evolution. Does that include a little bit of minor accretion and maybe minor mergers? Oh, well, I don't know. But anyway, in a reasonable environment that allows a little bit of accretion and a little bit of minor mergers, thick disk is naturally produced in most of the galaxies. Okay? And thin and thick disks are continuous rather than distinct. They are continuous products. They may appear bimodal and distinct, but the way, I mean, if it is bimodal, it's probably because it was due to a little bit of important event, just like Florent just mentioned, right? Otherwise, it could be continuous. Otherwise, it could be 3 peaks or maybe 4 peaks. We have all varieties of stories. So this is the Gaussian mixture model once again, as J.K. burnt just the last few days here with me. And on 6 galaxies we have here for your example. And if you have random 6 components detected in this Gaussian mixture model machine learning technique, and then on this galaxy you have thin and thick disk component, good. The other one, thin, thick, thicker disk component, 3 disks. This one, very thin, relatively thin, and thicker, and another thicker, 4 disk components. 2 components, 3 components, 3 components. If you believe machine learning, right? So just I don't believe in just 2 things. The universe is made up of disk or bulge galaxies. Galaxy is made up of bulge or disk. Or maybe the disk is made up of thin and thick disk. There's got to be more than 2, right? This is the lesson I learned. Thank you very much.
Thank you. It's mesmerizing to watch these simulations, and I was wondering, when you go from dispersion dominated to rotation dominated so suddenly, like what happens to the entropy? It's extremely counterintuitive that this phase transition happens, and you go from a disordered phase suddenly into highly ordered phase.
Yeah, it's one question I didn't want to have. Because the goal of this project, New Horizon, from the beginning, from the state of writing the proposal, was to understand the physics of disk settling. And it's been now nearly 5 years since its completion, and we are still fighting to write the draft. We haven't succeeded in writing the paper. And I don't know, maybe Christoph can explain his view. It's like a metastable stage of Q around 1. Once a galaxy reaches a certain mass, and where the Q parameter becomes roughly about 1. Once it happens, and then it actually self-regulates, it continues to form the stars, and some of the stars are disk heated. But I think I'm not really qualified to give any explanation any more than this. I think Christoph can say.
Just one word at zeroth order. I mean, this is an open system. You just injected a lot of cold gas into it, so the entropy has decreased because you've injected. It's the argument of the increase of entropy is for closed system. This is obviously not a closed system.
But if the injected gas, that's the question, like how much? So that if this happened so suddenly, so during that short time, did you double the mass or triple the mass of the galaxy?
No, that's not the case. Yeah, but mass doesn't increase abruptly. Yeah, mass increases, but if you look at this panel, there is a big mass increase between any panel, right? So it's not just mass. We try to point out the driving property, but it was not very easy. But at least what came out very clearly was the next slide. When disk settling happened, it was the stellar mass was about 10. It's a very magic number, and standard deviation was very small. But of course, this is very much dependent on the resolution effect as well. So if we raise the resolution, it might change. I think it'll become smaller. But anyway, there seems to be some mass effect. At least.
Hi, thanks for the wonderful talk. I just have a question on. I was wondering if it is possible to study how star formation activity affect the physical properties of the disks using the simulation. Especially, I'm wondering if it's possible to trace the gas circulation in these regions with different snapshots.
Yeah, it is possible, and we are doing it. Gas is very important. If gas supply stops or diminishes, then thin stellar disk cannot be maintained, and there will be only disk heating available, right? So if all of these galaxies maintain thin disk, that means now new stars are always born on the thin disk coming from the molecular clouds. We don't have molecular clouds in this simulation, so we have to do something, right? Subgrid physics. But the forming new stars on laser thin disk and then natural disk heating afterwards, they compete with each other, mysteriously maintaining Q parameter about 1. That's what we find. I don't know whether it's a physical explanation at all, but that's what we find in this experiment.
Does the strength of star formations, say local star formation rate, affect your physical properties of the thin disk and thick disk?
So, for example, a galaxy cannot settle a large-scale disk when star formation rate is very high. The nice thing about the New Horizons simulation is we have temporal resolution of 15 million years. We have 1,000 snapshots, right? So we can see the motion of gas in stars, in fine steps. And if gas flow is diminished, then there is no further thin disk. The mic migrates. Yeah.
On this slide, it's a short question, but so you said that if you were to increase the resolution, you would expect this settling mass to go to the left side of the plot.
That is my suggestion.
But you have the New Horizon 2 with poorer resolution, so
That's
you should
right.
expect that it goes to the other direction.
That's an excellent question. So in my New Horizon 2 simulation, a lot fewer galaxies settle their disks in time. Good question.
So anyway, first of all, thank you for your excellent work. I just wonder whether it is correlated with the disk warping. I mean, thick disk and thin disk, which one are more prone to be warped? And warping is believed to be in classical theory to be generated by misalignments between the angular momentum of baryon parts and the dark matter parts. So can you answer that?
Yeah, good question. We haven't paid any attention to that, but one thing I can tell you is most of our galaxies seem to be warped. Yeah. Ah. Okay, we can talk probably afterwards. Yeah.
So I think you gave us a warning that not to trust profile fittings. Do you have any suggestions then?
Oh well, I was very irresponsible, right? Yeah. Yeah, without telling you the alternative medicine. Oh well, we are trying a lot of profile fitting as well, and for profile fit, we have an archive paper on that. For massive galaxies, profile fit can give you a very good approximation, but once the mass becomes a little bit smaller, and then the profile fit, at least in our exercise, for which we have written the whole paper, the recovery rate was not very good. We can discuss that in detail afterwards.
And then finally, any comments on bars? No? Okay.
That is another question I wanted to avoid.
Okay.
No. This is an important, very important question. New Horizon Group has written a dedicated paper on bar. Having said that, I mean, New Horizon probably is the only reasonably large scale cosmological simulation that doesn't have a bar galaxy. Right, so we have a very high resolution simulation. This is a high resolution simulation, but we have one bar, but it later disappears. So
no, I feel I need to how should I say this?
Okay, go
correctly?
ahead.
All cosmological simulation with that resolution have a big problem. None of them have bars. We have one small bar.
That's what I was going to say. So, you know, the simulations like TNG 50 and so on, they do have lots of barred galaxies, just like observed. But the highest resolution simulations we discussed today, for example, none of them has a bar. So the Reddish et al., we were honest and wrote about it. And whether it's, I mean, it's a problem. It's a big problem, and I don't know why. I'm sorry. Yeah. We speculate on why in that paper, but it doesn't mean that I agree with the first author with that. Yeah.
All right. Thank you very much, Sukyoung.